Hello and welcome to this lecture. We're going to start looking at rational functions in this short lecture. Okay, so what are rational functions? So you see here, let me stop this for a while. So you see here, this is a form of a rational function. Rational function has a numerator which is a polynomial divided by a denominator which is a polynomial. The numerator may have a degree n, the denominator may have a degree m, and you have all these coefficients. We generally think of these coefficients as being real or complex, sometimes mostly real. Okay, so these find a lot of use. I mean, a typical picture of a rational function may look like this. So you see here, this looks a little bizarre, right? I mean, maybe you don't see clearly what's going on. If I even run it, so what I'm doing here, I'm changing these coefficients. I think I can't recall the degree here, some small degree numerator and denominator. You see here, as you change the coefficients, notice how this function is behaving in some bizarre ways. Let me see if I can stop it somewhere where it's a little bit more reasonable, maybe this one. So you see here, around this minus 10, there is a point where this function seems to be blowing up, right? To the left of it, it's going off to plus infinity. To the right of it, it's going off to minus infinity. And then it goes to 0 here. And then again, there is a point here where again it's blowing up, right? It's blowing up so that, to the left of this point, somewhere between, minus 2.5 or something, left of this point is going off to infinity, right of this it's going to minus infinity. And then again here, there is a point here around 7 or something, where again this infinity happens, but this seems to be much more sharp, around here, while these are a little bit more clear. So maybe, that just depends on how the coefficients work out. There's another 0 here, there's another 0 here, and so on. Okay, so what are these zeros and points at which it's blowing off to infinity? These are called zeros and poles. So zeros are roots of the numerator. Okay, so the roots of the numerator, the function itself goes to 0. Poles are the roots of the denominator. So when you have a root of the denominator, at that point, this entire function will blow up to infinity. And to the one side of it, it will go to plus infinity. The other side, it will go to minus infinity. It depends on how the signs work out when that value is substituted in the rest of the function. Okay, so this is how a rational function generally behaves. This is how the behavior is, and it seems like poles are quite bad for a rational function, right? I mean, poles make it blow away, blow up. It's true, poles you have to sort of avoid. In the region of interest, you may get some nice shapes, and how do you control that shape and all that depends on the coefficient. So you can see here, if I let it play for a while, you'll see that it goes all over the place when I change the coefficients, and these things transition from one to the other. It's just interesting to see these kind of plots and then see how the various pictures may turn up being. So you see here, the two poles here are very, very close, and they seem to be blowing up in one direction, right? So this is a slightly unusual sort of picture where blowing up in one direction, it's positive on both sides, right? So it's not going that way, so the pole might be really, really close and things like that. Okay, anyway, so this looks quite complicated and it's not clear how to think of it, and it turns out one can simplify the understanding of partial rational functions by doing something like a series expansion. Okay, so first thing is, series expansions are always useful because anyway you get a power series 1 plus x squared like that, and then eventually it converges. You can use it in various ways. Okay, so how do you do series expansions for rational functions? How do you try and understand them better? Okay, so for that, the first starting point, once again, all our topics so far, we have started in a small place, use some simple result, and then complicated it, and got better and better results. Same approach follows here. Everywhere you follow the same approach, right? So the simplest rational function for which we already know a series is a geometric series. Okay, this is you've seen it several times. 1 by 1 minus x is 1 plus x squared, so on, and this is true for mod x less than 1, right? This is also true for complex, by the way. You can make x as a complex number and you will get 1 by 1 minus x. The same thing would be true mod z less than 1. So this is a interesting result to remember. So this geometric series is very useful starting point. So for a rational function, see, 1 by 1 minus x is a rational function, right? Numerator is a constant polynomial, denominator is polynomial of degree 1. So this is a rational function. So it has a power series expansion of this form. Okay. So how do you extend this to slightly more non-trivial things? The first thing we'll look at is 1 by a minus x. This a is not 1. Okay, maybe a is different from 1. Then what you can do, you can divide throughout by a. Then you will get a 1 by a by 1 minus x by a, right? And then this you can rewrite as 1 by a into 1 by 1 minus u, where u is x by a. Okay, so I got this u here, and this 1 by 1 minus u is this form. Okay, once again we took a slightly different problem, did some basic tricks to get a the basic result, I mean the old trick back again. So once you get this 1 by 1 minus u, I know how to do an expansion, and I do that. So this is 1 by a into 1 plus u squared for mod u less than 1, and then now you substitute back again, you're going to get 1 plus x by a, x squared by a squared, so on, and mod x less than mod a. For this, if this condition is true, then this series 1 by a minus x is just this guy. Okay. So I hope you see this. This is a easy enough result to see. So we have managed to get expansion for 1 by a minus x. Okay. What do we do with more general rational functions, right? More general rational functions may not have, constant in the numerator and degree 1 in the denominator, right? How do we deal with a more general scenarios, right? So that I think is something very important. By the way, I just want to point out, even if this is of the form, a plus x, you can do sort of the same thing, and then you can take plus minus of minus x, and then repeat the same thing, and this series now will be like minus plus like that. Okay, so these things are small changes. As long as mod x is less than 1 and mod x is less than mod a, you can always have a series expansion of this variety. Okay, so this is very easy. How do we do for general rational functions? If I have a high degree numerator, high degree denominator, how do I use this to do for a general rational function? Okay, so slightly extending, we extended from 1 by 1 minus x to 1 by a minus x. Now we will extend from 1 by a minus x to a more general looking rational function. Okay, so we will start once again with a slightly simple case. We will start with a case where the rational function fx has a numerator, okay, which is maybe arbitrary, and then the denominator looks like this, right? a1 minus x into a2 minus x into ak minus x. Okay, now this means the denominator has degree k, and these a1 to ak are all distinct. Okay, now remember this if you multiply out, you will get a degree k polynomial. So if you take a degree k polynomial in the denominator, right, it may or may not factor like this into k different linear factors, right? So it depends on how the roots work out. Sometimes the roots may be repeated, sometimes the roots may not even be real, they may be complex. All sorts of things are possible here, right? But let's assume that this is the simplest. Let's assume this case. This is one of the simplest possible cases, and in this case you will see we can do a very nice trick called partial fraction expansion. Okay, so this is a very useful trick to understand rational functions. Partial fraction expansions are very, very important. But notice the assumptions I have made here. I have assumed the denominator factors into k different linear terms. Okay, that's a big assumption, may or may not be true. If it is not true, what to do? We will see that later, right? So for now, we can even assume these are real, for instance, if you want simplicity, but this being complex is not very different, it will be very, very similar. But another assumption I am making is that the numerator has degree less than k. The denominator has degree k, numerator has degree less than k. Now this is not a very serious assumption. Numerator can have a higher degree. You can always do polynomial division and convert it into a quotient into this denominator plus some remainder, and that remainder will have degree less than k. So using division you can deal with it. I will show you an example maybe later on when we do a problem, but that's the basic idea here. So this, while looks like a restrictive assumption, it's not too bad an assumption. Okay, the only thing that is restrictive is these a1 to ak are distinct. Okay, this may not be true. I mean, you may have repeated roots. You can have x minus 1 whole square or something, right? So that is possible. That case is not being covered here. That's the only thing which is not there. But pretty much otherwise, this covers a lot of interesting cases. Okay, so I hope this part is clear. So this is the case 1, as I'm calling it. So this is a simple case. For this case, it turns out partial fraction expansion is very simple, and we can do a very nice study of rational functions. Okay. So it turns out this is the main theorem. There exists constants C1 to Ck such that any numerator of degree less than k divided by product of k linear factors in x can actually be written as C1 by A1 minus x plus C2 by A2 minus x plus so on till Ck by Ak minus x. Okay, so this is a very nice and simple result. So I don't have to bother about product of several linear terms in the denominator. They just become sum of each of these linear terms. As long as the degree here is less than k, I only get constants in the numerator. So what we saw before, this 1 by a minus x is enough, right? If you do 1 by a minus x, you can do pretty much many other rational functions which have this form, right? So you can do, you can do series expansion for each of these separately and then add it all up, and you will get the series expansion for this. So this is a nice enough thing to understand. Okay. By the way, I should also remind you, these rational functions are not just for mathematical theory. The Digital signal processing, for instance, uses these things extensively. So do pay attention when you come to those kind of difficult courses. This topic will be very, very useful for you. Okay. So how do you find the C1 to Ck, right? So this thing is just says there exist these guys. This is sort of a proof which will also help us find the C1 to Ck. You can multiply both sides by this product, basically the denominator, right? This is product I equals 1 to k, ai minus x. The product of all these things is just the denominator here. If I multiply both sides by that, this is actually this guy. You will see left hand side will just be the numerator. Here I will have C1 times all these terms except a1 minus x. a1 minus x will not be there. So I will go from 2 to k. And in C2, you will have all these terms except a2 minus x, because a2 minus x would have gotten cancelled. Okay. So I equals 1 to k, I not equal to 2. The last term will just have Ck times product I equals 1 to k minus 1, ai minus k. The kth term will not be there. So anytime you have a Cj, that jth term is not there, x minus aj is not there, aj minus x is not there, everything else is there. Okay. I hope you see this simple relationship. Now once you have this, this becomes k equations and k variables, and you can show, I mean this part we will not show in this class, but you can show it has a unique solution. Okay. So once you know it has a unique solution, it's very easy to find that unique solution, and we'll go ahead and find it. So this is sort of the proof, I mean very sketch of the proof. I've not shown this crucial thing, that this k equations, these are k linear equations in k variables. Okay. So how do I get the k equations? By the way, so you have the constant term here, you can equate to the constant term here. The coefficient of x you can equate to the coefficient of x here, coefficient of x square you can equate to the coefficient of x square. So until coefficient of x bar k minus 1 you can equate to the coefficient of x bar k minus 1. You can try it for small examples, I will show you in small examples soon enough. But this actually becomes k equations in k variables, C1 to Ck, okay, linear equations. And we know how to deal with that, so you can actually show that they have a unique solution. Okay. So that's an important point. So what is the upshot of this theorem? The main point is a more general rational function actually becomes like 1 by a minus x once you simplify it. Okay. So you see our general approach is always the same, right? You start with a very simple result and make bigger results look like the smaller result, right? So that's the general idea behind all of this development. Okay, so how do you solve for the coefficients? Here is a repetition of that idea we had before. F of x is this guy, which is C1, and I multiply it throughout by the denominator here, and I get this expression. So here, if you put x equals aj, this is the really nice trick here. If x equals aj, all the terms on the RHS will go to 0 except for the Cj term, right? Cj term, why doesn't it go to 0? Because it doesn't have aj minus x. So that alone will survive, everything else will go off to 0. So you will simply get Cj term. So you see here, if you put x equals aj, the left hand side becomes equal to just Cj times product I equals 1 to ki not equal to j, ai minus aj, right. So instead of x I have put aj, all these ai products will come, this alone will survive. Any other term of this kind, because I equals j is there, it will go off to 0. Okay, so we get this expression here, and you can see why Cj alone survives. So now from here we get Cj equals this numerator evaluated aj divided by this product I equals 1 to k, I not equal to j, ai minus aj. Now this seems like a tricky form, you would keep remembering what it is, but you can remember this very, very easily. In fact, if you take f of x and multiply by aj minus x, notice what I have done here, you take f of x and multiply by aj minus x, what will happen? All the terms in the denominator will survive except aj minus x, right. This aj minus x will cancel on both sides. So you will get exactly this form, okay, and you evaluate that at x equals aj. Okay. So this is a trick that people use to find C1. What do I do? To find C1, I imagine this f of x, I forget about this a1 minus x, put x equals a1 and evaluate it everywhere else, that guy will be equal to C1. How do I find C2? I imagine this guy without this a2 minus x, this is gone, and then I put x equals a2 in the remaining things, whatever that is C2. Okay, so this is a very easy way to remember how to find the partial fraction expansion for these kind of terms. Okay, so I hope this is clear. You can solve for the coefficients. Okay, so let's see a bunch of examples. So I'll do some of them real quick. Let's start with the easiest of case 1. So I won't do the second one, it's very simple. I'll do the first one, which is even simpler, just so that I can do, I can get away with it very fast. X minus 1 by x squared plus 5x plus 6, I think that's the one. Okay, first thing is you can quickly factor the denominator. You see that that is x plus 3, x plus 2 into x plus 3. Okay, and I know this will be something by x plus t plus x plus 2 and something divided by x plus 3. How do I find the coefficient of x plus 2? Forget about this guy. Okay, forget about this x plus 2. Put x equals minus 2 in these things. So, it will be minus 2 minus 1 divided by minus 2 plus 3, right. That is what it is. Now, for this guy x plus 3, I will forget about x plus 3 and put x equals minus 3. So, minus 3 minus 1 divided by minus 3 plus 2. Okay. So, that is minus 3 by 1. So, it is minus 3 by x plus 2 plus this guy is minus 4 by minus 1, it becomes plus 4, 4 by x plus 3. Okay. Okay, so you can quickly check that this will give you the exact same thing, and we got the coefficients very, very easily. From here, you can go on and find the series expansion if you like. You know, this has got a 2 plus x, so if you want the series expansion, let's say 4 by x plus 3, it will be 4 minus x, and you will get here 4 by 3 into 1 by 1 minus x by 3, and you just put that in the expansion, you're going to get 4 by 3 into 1 plus minus x by 3 plus minus x by 3 whole squared, so on, and this is true for mod x less than 3. Okay, so this way you can get the expansion if you like, and you can do many other things in this fashion. Okay, so that's one thing, and I mean, this one I'm not going to do, it's very, very similar. You can do it very easily. Case 2 is unique complex roots. It proceeds in exactly the same fashion. Just for comfort, I'll show this simple case. You have unique roots, but some of the roots may be complex. Complex or real, it doesn't really matter. X minus 1 by x squared plus x plus 1. The method really works, you know. So, it's just x squared plus x plus 1. We saw the roots here will be, you know, we saw this omega equals minus 1 plus root 3 by 2, I mean root 3i, I'm sorry, and then omega bar, which is also omega squared in this case, right. So, we know this minus 1 minus I root 3 by 2. Okay. So, this is these are the two roots here. So, this kind of notation is easier to handle than, you know, carrying on this minus 1 plus I root 3. You can just put this out here. It will work out quite well. You know that this is going to be x minus omega into x minus omega squared. Okay. So, now this again will come out as x minus omega plus x minus omega squared. I'm going to forget about this guy and put x equals omega, and the remaining of them omega minus 1 by omega minus omega squared, and then I'm going to forget about this guy and put omega equals x equals omega squared, and the rest of the one, so omega squared minus 1 by omega squared minus omega. Okay. So, you can simplify this, pull the omega out, you're going to get 1 minus omega, so you'll get minus 1, and we know 1 by omega is the same as omega squared, right. See, omega cubed is equal to 1, so 1 by omega equals omega squared. So, so you'll get just minus omega squared, if I'm not wrong, omega squared, yeah, minus there's a minus 1 because of that. So, you get x minus omega plus here you know, this is omega squared minus 1, you've got omega minus 1 here. So, we'll end up getting 1 plus omega plus 1 divided by omega here, and now omega plus 1, if you remember, is minus omega squared. So, you end up getting minus omega by x minus omega squared. Okay. So, you can check this, these calculations are not so important, please check. I might have made a mistake here. So, you have to use the two of the facts, 1 plus omega square is 0 and omega power 3 is 1, and you can simplify these things and you will get an expansion like this. So, you see here, and after this you can do power series expansion just like you did before, and nothing stops you from doing that. You will have a complex series and it will converge when absolute value of the complex variable is this. Okay. So, you are thinking of x as a complex variable here. I know this is a real function. How is this working out as a complex thing? So, it does not really matter. In fact, if you see this and these are conjugates, right, in some sense all the coefficients are conjugates. So, if you put a real number here, these two will become conjugates of each other, because the real number does not change whether you conjugate or not. So, they will add up to give you a real number. Okay. Even though this is complex, this will be complex, this will be complex, the sum will be real. Okay, you can check all these things. It's very nice. It has to work out, right? Because the left hand side is real. This thing better add up to be real. Okay, so this you can sometimes use to simplify your calculation. When you find this, you can just simply conjugate it and you'll get the value. Anyway, you have to be careful about these things, but these are ideas that you can use. Okay, so complex roots we can handle quite easily. Here you will have one part of it being real, the other being complex, but the method is largely the same. Okay. What about higher degree numerator? Okay, so let me take the second part here. It's easier for me to write down than the first part, so I'll do the second part. X cube plus 1 divided by x square plus x plus 1. So here what you should do is actually very simple. So you're looking at x cube plus 1 divided by 1 plus or x square plus x plus 1, right? So the only problem I have here is degree of the numerator is greater than 2. I don't like that, or even if it's equal, I don't like that. So what you do is you use the division algorithm, right? So you might remember this division algorithm of polynomials. So here I have to put x here, I'll get x cube plus x squared plus x, and then I have to subtract, this will go away, 1 minus x squared, or maybe let me write it like this, minus x squared minus x plus 1, and so I would put a minus 1 here, so you get here minus x squared minus x minus 1, so you add these two, subtract these two, you're going to get minus 2, plus 2. Okay. So what you get here, what does this division algorithm mean? This is the remainder, this is the divisor, right, the one you divided by, and this is the quotient, right. What does this mean? It means x cube plus 1 is the quotient times the divisor plus the remainder. Okay, that is what this means. So instead of x cube plus 1, I can put x minus 1 into x square plus x plus 1 by 2. Okay, so that's what the division algorithm has given you, divided by x squared plus x plus 1. Now you divide this in term by term. So you write it as x minus 1 into x squared plus x plus 1 divided by x squared plus x plus 1 plus 2 by x squared plus x plus 1. These two cancel, so what you have here is just a polynomial plus 2 by x squared plus x plus 1. And we can now do partial fraction here. Why? Because this reminder's degree is going to be less than or equal to degree of divisor. Not less than or equal to, I am sorry, strictly less than degree of divisor. Okay, that is the power of the division algorithm. So if you have a numerator which has a higher degree than your denominator or greater than or equal to the denominator, you do one operation of division. And then you will go to a remainder which has degree lesser, and the quotient part will just be a polynomial. The polynomial is just a polynomial, right? It will affect the series expansion only a little bit. Okay, and then beyond that you will have an infinite series which is given by this guy. Okay, I hope this method is clear. You can use this if the degree of the numerator becomes larger. The only confusing case is if you have repeated roots. Okay, so in this case things become a little bit more complicated. 2x plus 1 by this case is repeated roots. I'm not going to do it in great detail, except just telling you how the form of the thing will look. If you look at 2x plus 1 by x plus 1 whole square x minus 2, 2x plus 1 by x plus 1 whole squared into x minus 2, right? Let me just check that. Yeah, so I'll write down just the form of the distribution, this form of how this will look. You will have c1 by x plus 1, but you will also have a c2x by x plus 1 whole square, and then you will have c3 by x minus 2. Okay, so this the c2 and c3 you can find in some reasonable way, but this finding c1 is a little bit more confusing, so you'll have to do some other tricks like differentiation, this, that, and the other, and it's a little bit more dicey, but you can do that. And what do you do for terms like this? How do you expand 1 by x plus 1 whole squared as a power series? Okay, this is also a bit tricky, so you'll have to do some differentiation, and it will be like a different form of the power series. Okay, so basically this is a slightly more complicated case when you have repeated roots. I will leave it to you to look it up, or when we have an advanced course, maybe later on we can see this in more detail. But repeated roots are a little bit more complicated. You can do the same thing, but it's not exactly similar to what we've done before. You do a partial fraction expansion with more work. Okay, but generally in this class we'll bother mostly about the first three parts, mostly case 1, and you may have complex roots and you may have a higher degree numerator. Okay, So that gives us partial fraction expansion. Now hopefully you are convinced that partial fraction expansion converts a complicated looking rational function into a simple sum of linear terms. And each of those terms you can understand well, and this you can use for visualization, for plotting, for differentiation, integration, approximation, power series, anything you want, you can use this. So once you see, because once you write this rational form in terms of this partial fraction expansion, you can see differentiation is easy, integration is easy, everything is easy, right? Integration will give you a bunch of log terms, differentiation will give you like minus 1 by x squared terms. Very easy to do. Power series also. Okay, that's the end of this lecture. Thank you very much.